right, exponential equations today. I'm going to save the logarithmic equations for the next video, so we'll just be doing half of this lesson in this video. First up is a very basic exponential equation. It's where you're going to have an exponential expression on both sides of the equal sign. So we're going to use the one-to-one property to solve this. What's going to happen is you're going to have something raised to the power on one side, and then the same base, the same exponent base on this side. So whenever that happens, if you want to think of it as they cancel, I guess that's all right. We're actually taking log base b of both sides and using a one-to-one solving property. The only way that these two things are going to be equal is if their exponents are equal. So let's try that. We'll try to work our way up from this example. So I'm looking at this and both of my bases are the same. So in order for this to be a true equation, whatever is in this exponent on the left side has to be equal to what's in the exponent on the right side. So I'm going to subtract 2x from both sides. It doesn't really matter which side I move my x's to, but this is just solving like we had back in the beginning of the semester. Add 3. I get 10 is equal to 3x. Divide both sides by 3, and I get 10/3 is x. I can definitely solve, or I did solve it. I can definitely check my answer by plugging this 10/3 back in for x on both sides of the equation. So I'm going to add one step to that. That one was pretty easy because the bases are already matched. Here's how I do it if the bases do not match. What I want to do is I want to use my knowledge of exponents and stuff being raised to the power to make it so that both sides of the equation have a common base. And then from there, once I have this common base, I'm just going to set my exponents equal to each other thanks to the one-to-one property, and then solve for x. So let's up it just a little bit. In this case, I have 5 to the x equals 125. So I want to look at my smaller number of the two, this 5 to the x right here. I want to see if there's any way that I could write 5, or in this case 125, as a smaller base being raised to an exponent. In this case, I can. The 125 can be raised, is the same as 5 raised to the 3rd power. Now my bases match. I have a problem just like the last one. I get x is equal to 3. Let me get you going on part C. On part C, I want to make both of those bases smaller. I can't think of 27 raised to what power gives me 81. I don't know what that is. So that's not going to happen. I'm going to need to lower both of these. Okay, so I'm looking at both bases, thinking about the 27. How can I write that as something raised to a power? Well, it's going to be 3 raised to the 3rd power. Notice my use of parentheses right here. Just bring those over. Okay, that's 81. I can have the same base, 3 raised to the 4th power. And then from here I solve. I'm going to let you go ahead and solve that, and then play what you've done to see if we get the same answer. I got 8/5 for my answer on that. Okay. Now, we're not always going to be able to manipulate around the bases. I call those simple problems. Okay? I want to put one of those in your quiz, help you out. Make sure you can manipulate that base to get it to work. But the bases won't always match. Okay? And so when you can't get the bases to match, if you're just dealing with one exponent, here's some ideas. First of all, you can isolate the exponential expression. Okay? Make it so the only thing that's on one side is something raised to a power. Okay? Next, I can just take the log of both sides. That's another great option. If you have x up in the exponent, taking the log of both sides will get that x out of the exponent. We'll see that on the next example. Use your inverse properties. Use your definition of logarithm. Definition of, I guess exponential would be the same as definition of logarithm, being able to move back and forth between the two equations and to finally solve for the variable. So let's take a look at example 2a up here. As you can see, I really can't match these bases, 7 and 6. I can't say 7 raised to some power gives me 6, 6 raised to some power gives me 7. I could, but it's a very complicated exponent as to how to get there. And so what I've done on each side is I've isolated the exponent. I've made it so the only thing on one side of the equation is something raised to a power. So I can't simplify that anymore. But the problem is I'm trying to solve for x, but x is hidden up here in these exponents. So to remedy that, I'm going to take log, or I could take natural log of both sides if that works better for you, whichever one you want to do. Now, the whole reason I'm taking log is that I can use my power property now to drop the x down in front of the logarithm. In this case, the exponent is x plus 5. It drops down. Now I don't have to worry about any exponents in this equation. I do want to get rid of my parentheses here. So I get x log of 6 plus 5 log of 6. I just distributed log of 6 to both sides. Same basic algebra rules that I've always used. Get everything that has an x on one side of the equation. Everything that does not have an x will stay over here. And the whole idea of doing that is that you have a greatest common factor of x that you can pull out. So you've knocked this thing down to just a single x. Divide both sides by these parentheses. And notice I haven't typed anything into my calculator yet. I'm going to save all that fun thing here. Because whenever you work this, I want both your exact answer, which is exactly what I just wrote down, and I want a 3 decimal approximation on it. So 5 log of 6 divided by log of 7 minus log of 6. 58.117. You try part B. Use my work over here as a template. This is about as hard as I can make an exponential problem in this class. So I want you to try part B. Use this as a template, and then you can come back and see my work on it once you're done. You can play it. This was my second time through on this video, and the whole idea was this problem. I forgot this pesky little negative sign right here, which made the problem come out to be positive. So pretty sure this is the answer this time. Hope you got it. Like I said, that's about as hard as I can make these problems. Let's only do something that's a little bit easier before I sign off. Oh, Mr. Noise showed me this trick. You just draw a circle around the whole thing and got it. Man, that is so cool. Thank you, Jordan Noise. All right, so now if I don't have two exponential expressions in this, I think the problem gets a little bit easier to work. Okay? For instance, on this one, I just have e to the 3x. I want to treat that e to the 3x as my variable up front. Okay, so I want to make it so that this e to the 3x is the only thing that's left on the left side of this equation. So I'm going to add 11 to both sides. I get 5e to the 3x equals 3. Divide by 5. I get e to the 3x equals 3/5. Now, there's a couple different ways you can think about how to solve this from here. You can take the log of both sides and drop this in front. It's going to be kind of a mess, but I think that if you think of it in terms of writing it as a logarithmic equation. So remember this e comes over and hides underneath the log on this side. I get this. Well, I don't want to see the log base e. We have a very special name for that. So I'm going to write this as the natural log of 3/5 over 3. That would be my exact answer. Let's type this in the calculator and see what we get for our decimal approximation. Natural log of 3/5 and then divide by 3. Negative 0.170 to 3 decimal places. Got one more. We got multiple e to the x's on this. We actually have an e to the 2x. So we're going to be a little bit careful with this. E to the 2x. Now, we've worked a problem like this before. I want you to see the similarities between this problem and u squared minus u minus 12 equals 0. Okay? it is the same problem. We're still going to factor it just as we factored this u squared minus u minus 12 equals 0 back at the beginning of the semester. So this e to the x right here is actually e to the x times e to the x, the same way that this u squared is u times u. So whenever I go to factor this, I can split apart this e to the 2x as e to the x and e to the x. And then from here, I just want to think of two factors of negative 12 that add up to give me negative 1. Negative 4 and positive 3. I've got this factored now. That means that either e to the x minus 4 equals 0 or e to the x plus 3 is equal to 0. So if I add 4 to both sides and then change this to a logarithmic expression, I get log base e of 4, which is just the natural log of 4. Go ahead and type that in my calculator. Natural log of 4 is 1.386 is what I got. Over here, I do the exact same math with this. Take the natural log, my x is going to equal the natural log of negative 3, and ooh, red flag right there. I cannot take log or natural log of negative numbers. So over here, I get no solution. Okay, so this right here is my only answer. Even if you did forget, you try to type in natural log of negative 3 in your calculator, you're going to get a domain error. And so it will fix itself. Good luck on the homework. Let me know if you have any questions. And some of these up front, my students said they're kind of trickier. A couple different ways to solve them on there. Just kind of play with them and use what you know about exponents to get the correct answer.